Our next presentation is microgravity with electrical capacitance tomography, and the speaker is Jed Storey.
Okay, so I'm going to be talking about preliminary results from propellant mass gauging and microgravity with electrical capacitance tomography. These are the people who worked on this project. So me, then Brandon Marcel, who's the branch chief of the LSP Environments and Launch Approval branch, Mike Elmore, and Scott Clark. I'm going to go fairly quick through the first half of this presentation so we can get to the results. I was a little ambitious with the number of slides, so I will summarize many of them. So one of the big problems right now is propellant mass gauging, microgravity. A lot of the propellant mass gauging technologies that are designed to work in an accelerated environment don't necessarily work well in a microgravity environment. And I list some of the various mass gauging technologies there. They all kind of share two things. One is they all have at least one major drawback, and the other is that they're all fairly low accuracy, where I'm defining low as something like 3%. So we really need a technology that can address these issues for microgravity. So there are a lot of impacts from improving mass gauging. So if you can improve accuracy and precision, it results in more accurate propellant utilization tracking, lower propellant mass dispersions, lower required residuals and margins for filling and topping, as well as final residuals. So an example of what this might affect is if you can improve the final residuals and mass dispersions, it means that you can have more informed decisions on whether or not to perform a deorbit burn for say a second stage of rocket, right? And that is the potential to reduce orbital debris. There's also big advantages to enabling mass gauging during all phases of flight. So for example, say you have a launch vehicle during ascent, using a mass gauging technology that is immune to slosh would mean that you're able to track propellant utilization more accurately. And in space, if you could measure the mass without needing to settle, that has some obvious efficiency implications. So there are some benefits, major benefits to improving mass gauging technologies. This is where electrical capacitance tomography comes in. ECT works by measuring the capacitance between multiple pairs of thin conducting plates. And there's a cartoon of this on the right. Since capacitance is related to permittivity, which in turn is related to density is possible via tomography math to measure the distribution of liquid inside of a tank. And if those measurements are fast enough, this can be done in real time. And finally, integration of the density distribution yields the mass inside of the tank. And as the previous presentation talked about, ECT is not new. It was originally developed for the oil and gas industry to measure multi-phase mass flow rate in pipes, though it has been recently applied to tanks. So what really kicked all this off for me was I read this conference paper that was published by Philip Peruzzi et al. In July 2020. This showed an ECT system that demonstrated better accuracy over all fill levels than all current mass gauging technologies. In fact, they achieved less than 0.1% volume error for basically all of the tests that they ran. So that really inspired this whole project. I read into it more, and it turns out ECT has been tested in many different tank materials and different tanks, and it will theoretically work during all phases of flight. One of the more interesting advantages of this technology is that it has the ability to track propellant distribution inside of a tank in 3D, which could help prevent vapor pull through and liquid venting, and it may potentially allow for future advancements and open up these doors such as active slosh control. So if you can measure your liquid distribution in real time in 3D, you could theoretically put that inside of a loop and not rely on mechanical models of slosh. So there's a lot of potential for technology that can do this. However, it hadn't been tested in microgravity until now. So the primary objective of this project was demonstration of accurate liquid mass gauging in a subscale propellant tank using an ECT system during a zero-G parabolic aircraft flight. The secondary objective was to obtain the 3D liquid distribution versus time and use this in a CFD validation study. That's still ongoing. The expected TRL after flights was 6, and I believe we have achieved this, as I'll discuss later. And a tertiary goal was to encourage additional funding for ECT development work. So this was funded by an LSP study in 2021, and the NASA Flight Opportunities Program funded the flights on Zero G's G-Force 1 aircraft. We flew back in May 2022. And I want to stress that this was a demonstrator. We didn't design nor develop the hardware for this. So we demonstrated it and have used the massive amount of data that we collected to in our various analyses. So I'm going to talk a little bit more about the experiment first. These are a list of requirements. I'm not going to go through all of these, but obviously we needed an ECT instrument and test tank. We wanted to have some software that come with the tank that would show the currently measured volume or mass. We also wanted to record the raw capacitance data at a sample rate high enough in order to do the 3D liquid reconstruction stuff for future CFD validation. And I say 100 hertz here. It's just needs to be high enough so that when you low pass filter it to remove any sort of electrical noise, that you don't affect you don't get anywhere near slosh frequencies, right, with the low pass cutoff filters, so that you maintain the information related to your liquid motion. Those were like basic requirements, but Zero G imposes, the Zero G company, right, that runs the plane, the parabolic aircraft plane, they impose a lot of requirements, many of which come from the FAA. There's a real high level overview here, but if anyone ends up flying a Zero G experiment, you'll have to go through the payload user's guide and put together your payload integration package, or PIP, and all of this other stuff to show that you comply with these requirements. And then if you fly with the Flight Opportunities Program, NASA HQ requires all flight experiments to pass an air flight worthiness safety review board, in addition to all of the requirements that Zero G requires. So high level overview of the experiment design. Here's a picture of it. There's a secondary containment case in which the propellant tank, or simulated tank, resides, a laptop for data acquisition. All this is mounted on a frame, and this gets bolted to the aircraft deck. The pink is just part of the crate that ships this case around, so that doesn't get installed in the aircraft. This is the tank. It was a 2.8 liter aluminum spherical test tank, partially filled with a non-hazardous propellant simulant liquid. The tank has 8 thin internal electrodes, 4 in each half, which cover most of the inside surface of the tank. This box provides secondary containment in case of a leak from the tank. The laptop runs the data acquisition software, and then we, LSP, added a small single board computer with a 6-DOF IMU, which isn't pictured here, but it was bolted to the plate here, that allowed for collecting the motion of the aircraft, data related to the motion of the aircraft. Some more specifications are listed here. Propellant simulant selection. So I reviewed all 3 MFC and Novec engineering fluids in order to select a propellant simulant. I use these because they're all non-hazardous, non-toxic, non-flammable, and have no transportation controls, so they're really ideal simulants, liquids from that perspective. 3MFC72 was ultimately selected because it has the lowest dielectric, which is near 1.7, which makes it closest to the cryogenic propellants dielectrics, which range from 1.2 to 1.6. I also did a non-dimensional scaling analysis to assess fluid dynamic similarity between the simulants in the test tank, and then cryogens, compared to cryogens in a full-scale, say 3-meter diameter spherical tank. And it turned out that FC72 also has the highest density to surface tension ratio, which makes it the most similar in terms of Weber and Bond numbers to the cryogens in the full-scale tank. So this was really an ideal choice for a simulant liquid in this case. And a close second was Novec 649, if FC72 isn't available for you. So some pre-flight info. Before March of 2022, we were working on the payload integration package and all the documentation required for that. March to April, we generated test procedures and practiced them. We're in KSC, right? So we had to get the experiment to Fort Lauderdale, which is where the Zero G plane was flying out of for the May test flights. And so it arrived there safely, and we ran checkup tests when it arrived. And then we had to pass the test readiness review. There were 2 minor things to correct. We had to add foam around the frame for padding. And then we also had to label our kill switch, which is the power strip switch here. Really minor things. And this is a picture of the experiment installed in the aircraft, in the zero-G aircraft, which has a bunch of padding. And having this padding and all of the padding was really necessary because you have very little control of yourself and other objects when you're flying around in zero-G. So we flew on 4 flights. Each fill level had a different flight with a notional. Each flight had a different fill level with a notional volume fraction. So we did 5, 20, 50, and 80%. We had very precise knowledge of exactly how much liquid ended up in the tank, though we didn't have super precise control over how much liquid ended up in the tank. So that's why I call these notional volume fractions. So we didn't have a lot of control. It was probably 4 to 6% maybe, or say 19 to 22%. But we knew exactly how much we ended up within the tank, thanks to the way we were loading it. And then we flew on the 4 flights, and that consisted of approximately 100 zero-G parabolas, plus some lunar and Martian ones, which they fly those in order to acclimate the flyers to the parabolic motion. This is a long list of lessons applied and lessons learned. So lessons applied were things we learned from previous flyers and previous people who had flown experiments, and we implemented these, and they were all very useful. I'm not going to read through all of them, but one of the most important ones is bring in fly backups, because you never know who will get sick. We had one of our flyers get sick on the first flight, but luckily the others didn't, so that's good. And then we had some lessons learned, such as padding all of the frame members and anything really. You have to pad everything, your experiment. It's important for your experiment to not need to be unbolted and removed from the plane. In fact, you can't remove it from the plane. We had to unbolt it between flights in order to tip it up on its end in order to fill and drain it. There was no way to do filling or draining without tipping it up. So designing your experiment to not need to be unbolted is pretty important. These flights, it created a lot of hassle for the zero-G people. And then one kind of surprising thing that many people who haven't flown on zero-G planes may not know is that the zero-G parabolas are not steady nor consistent. This was actually good for our experiment because it generated liquid motion in the tank, but I can see how it would be very not good for other experiments. And the reason for this is that the pilots actually controls the zero-G part. There is no automated control for zero-G or the parabolic flights. It's all manual control. And then put as a GPS track in your shipping crate if you're shipping anything. The experiment got there fine. They actually lost it on the way back. We had to ship it because of liability reasons, and the shipper lost it on the way back. It ended up in Chicago. Fortunately, they found it, but this was a lesson learned. Here's a picture of me floating upside down while monitoring the data on the laptop. There were no incidents, no realized hazards. The experiment performed nominally. We didn't have any major errors. Collected a lot of data, good data, and the preliminary data checks look promising. The user interface on the laptop displays some data which we monitored during flight. So that's actively calculating the fill level % in the tank in real time. So we noticed that the transitions to zero-G cause significant liquid motion, as I mentioned earlier, and we observed swings of 1 to 4% volume fraction during zero-G, during the zero-G maneuvers. So you could see how the measured volume was changing of roughly this magnitude. Though the center of that swing wasn't necessarily the known fill %, and the swing amount depended on the fill level, and each parabola was different, as I mentioned earlier. So this was our first kind of look at that data. I'm not going to talk a lot about the analysis stuff because I won't have time to get to the results. But key thing here is we didn't want to rely on the mass gauging calculations from the closed source software that came with the experiment, so we wanted to implement our own algorithms. So we ended up implementing 2, which won't mean a whole lot to people outside of the ECT community, but one is called linear back projection, which I think was mentioned in the last presentation, and another one's called Landweber, which is an iterative algorithm. These require generating what's called a sensitivity matrix as part of the algorithm. And to do that, you have to run some simulations. And so I ran some electrostatic simulations in Star CCM using the actual geometry of the tank. And this is the math. Again, I'm not going to go through all this. If you're interested, these slides will be posted so you can all this, but linear back projection basically assumes that because the S matrix, the sensitivity matrix, isn't square, you can't invert it directly. So it assumes that the inverse of the sensitivity matrix is actually its transpose. And you multiply that transpose sensitivity matrix times the normalized measured capacitances, which is this gamma or lambda. And then that results in a permittivity distribution, which is your liquid distribution. And despite the non-physicality of that assumption, linear back projection actually works surprisingly well. And then Landweber, as I mentioned earlier, is an iterative algorithm, and it's actually steepest gradient descent with the goal of minimizing capacitance residual, which is this term. And the end result is the same. It's a array of normalized permittivities, G, which range from 0 to 1, where 0 is empty and 1 is full of liquid.
Give me the time check. You got 5 more minutes.
5 minutes, great. Yeah. Okay, yeah, I was way over ambitious with this, but so this is an example result. I chose a time step a few seconds after starting data collection during our third flight. So this is when the aircraft was on the ground. The actual fill level was approximately 52.6%, and the experiment software recorded about 50% at this time. And so I simulated a case with a flat 50% fill level. In this image, the gravity's down here, so you can see the tank is slightly rotated about its axis. The gray image is the simulated surface. The blue image is the reconstructed surface from using Landweber from the experiment data. And the red is, which is basically directly overlapping the blue, is the reconstructed simulated data. So I ran the simulation with the gray surface and reconstructed it exactly how I reconstructed the blue surface, test data surface, and got the red surface. So the fact that the simulated reconstruction and test data reconstruction match so well means that the simulation is accurately replicating the physics. However, what's not accurate is this warping that's occurring near the edges, and that's due to high sensitivity, due to high electric fields and these gaps between the electrodes, and it causes the reconstruction to pull into those gaps, sort of. Though you can see the majority of the liquid surface is actually flat if you look at it from an ISO view. But this is an artifact of the reconstruction, this warping. Here's a slice through that view. Linear back projection results in a lot of smear. So this is where the liquid is, and this is where the gas is. And you can see that Landweber really sharpens up the interface nicely. And this jaggedness is due to the mesh. So this was roughly 1 mesh cell height. But the good news here is the calculated volume fraction was 50 to 51%, depending on how I did it, and the actual was 52.6. So it worked fairly well for this time step. Then I processed a time series, which I don't have a whole lot of time to talk about, but yellow here is acceleration, 0g up to hypergravity when it's pulling out. And these variations here in the blue line, which is the measured volume fraction, are variations due to the liquid moving from low sensitivity to high sensitivity regions inside the tank, and therefore is an estimate of the error, right? It's oscillating. The measured volume fraction is oscillating. Those swings were, the range for this fill level in this section here was 47 to 59%, which isn't great. However, I didn't do a lot of filtering on this. This has a 10 hertz cutoff filter, which maintains all of liquid motion. It retains all of that information. So, obviously implementing stricter filtering would crush that significantly, and you end up with much less error than that. Here's a plot of the mass error percent. This offset here from accelerated environment to in the accelerated environment portions during hypergravity. This offset has been fixed. I just didn't make it into this presentation before the cutoff for putting it into export control. But this offset has been corrected. And I have tried more strict filtering techniques, and that crushes this error percentage down to the 1 to 3% range. But this just shows the same chunk of time as the previous slide. This is a slide shows various error sources and improvements that could be done. I don't have time to talk all of this, but summary, the primary objective is achieved. The ECT sensor systems are useful as a propellant mass gauging technology in both an accelerated and microgravity environment. I expect significantly better performance if the previously mentioned improvements are implemented. Currently working on post-processing everything, all of the data, and implementing more accurate reconstruction algorithms, writing journal papers. There's actually one submitted already for a more accurate sensitivity matrix, and I'm working on one for a more accurate reconstruction algorithm than what's currently in the literature. What we're not currently planning is any further flights of this hardware. Just hoping to inspire other people to take up this technology. Thank you.
All right, thank you for that talk. We have a question in chat asking what the simulant fluent was again.
It was 3MFC72.
And one question that I had also, you said that the hardware came with some software for its own mass calculations. How did those results compare to the ones that you processed yourself?
Yeah, so we were seeing swings of about 1 to 4% depending on the parabola and fill level. And that percentage is volume fraction percent, so volume fraction of the tank. We were seeing swings of 1 to 4% plus or minus during the flight. So that's with the software that came with the experiment. In the slide, one of the last slides I showed, I was showing swings of maybe plus or minus 5%. So the agreement was fairly similar in terms of volume fraction percent swings, I think.